I'll just go ahead and start by introducing our first speaker, Chen Wang. And he's going to be telling us about dissipative quantum error correction of single photon loss in a bosonic qubit. So Chen, go ahead and take it away.
Am I screen sharing fine? Do you guys see the presenter mode? Okay, okay, awesome. So I'm Chen Wang from University of Massachusetts, Amherst. So that's the flagship state university of Massachusetts. And we on the screen, you're seeing our new, brand new physical sciences building that was just 2 years old. And my lab just got set up inside this building like about 2 years ago. Okay, we are a superconducting circuit lab, and you see dilution refrigerator running. And today I'm going to tell you about basically the first major experiment result coming out of my lab. This is on dissipative quantum error correction. Okay, and of course it's on a bosonic cat qubit or cat or binomial qubit. So I think in this conference you've heard quite a few times about dissipation. I just want to beat this drum a little bit more. And if you think about our classical information processing system, really the first gatekeeper against any noise in the system is dissipation. We don't really actually use active error correction that often. Dissipation is in some sense more essential. If you think about, say, a magnetic hard drive, things like that, right? When you have environment noise perturbing your little magnetic domains, oftentimes you have dissipation in the system that is used to dump entropy and align the magnets and stabilize classical information. So this is a fairly robust mechanism that is built in these physical systems. So the question is there any analogous process we can use for quantum states? Can we actually use dissipation to do error correction to correct, to stabilize quantum states, right? So there's actually, well, many people would think, okay, dissipation is often or typically bad, and which is almost certainly true. So there's a very big difference, or that means there is a substantial challenge of using dissipation in quantum system. In classical system, in order to store your classical bit 0 or 1, you just need them to be separated in configuration space, and you add basically 360-degree dissipation on each of these two configuration points. You just need a bistable system and you get a stabilized system. But in quantum mechanics, if we want to stabilize a qubit lives not in discrete points, but it lives in a continuum, in a 2D. This is a Hilbert space, like a block sphere. I'm representing this as in a high dimensional Hilbert space. Okay, and other outside the sphere or inside the sphere will be represented, will represent other parts of the Hilbert space. So if you say you use dissipation to stabilize my qubit, what you really need is dissipation that moves, that is orthogonal to this block sphere. It can drive states outside your code space onto the code space. And it's very important that your dissipation has to be orthogonal to the code space. If your applied good dissipation you're trying to do is driving your qubit around the block sphere, then that's spoiling your quantum information. So this means this dissipation has to be very specifically chosen, engineered, or even better, it has to be protected by certain symmetry in the system. And this is not even enough. Sometimes you come up with nice dissipation and you do this, you have a nice manifold, but what are you working against? Why is it helping you, right? The question you ask is, is my encoding space actually a good QEC code? You want a good QEC code where actually the dominant error represented by these gray arrows, these errors also need to be orthogonal to your code space so that these errors are error correctable based on your encoding, right? If you have your error that is not designed to be corrected for this code, then there's no hope you can use dissipation to correct this error, right? So combining this encoding requirement as well as this dissipation geometry, it means that the dissipation has to be very, very special or exotic for this to actually work in a real system. So over the years, there are a bunch of proposals out there, and there are growing numbers of them. So I already learned a few new ones on top of this list. So there are early designs of a dissipative error correction against the bit flip or phase flip. These are already relatively complicated reservoir engineering schemes, how to come up with smart dissipation. But even if you do an experiment to implement this, real physical errors, as you know in the system, may not be described by simple bit flip or phase flip. Even if you correct one of them, it doesn't necessarily buy you an advantage eventually, as long as until you do a next level of concatenation to get rid of the other type of errors, right? And there are newer designs, more complicated things against multiple or major physical errors in a system. And these typically need novel hardware to be developed. They often require new components to be developed hardware-wise. And these are really interesting ideas. There are certainly leading experimental groups working on these. And just as an illustration in terms of what kind of dissipation one may engineer, many of you have heard of this example, which is called two-photon driven dissipation, as initially demonstrated by the Yale group, and further on, Zaki moved on in his new institution now and has demonstrated an improved version of this two-photon driven dissipation. What it does is it stabilizes two coherent states. It creates a plus alpha state, a minus alpha state as a minimum energy state in the phase space, as well as all possible superpositions of these plus alpha and minus alpha state. So this dissipation will satisfy the condition that it does not drive your qubit crazy around the Bloch sphere. It does not spoil information, and it does suppress cavity dephasing type of error. And there are extensions of this that can work for 4-component CAD code. But there's one obvious issue with this, is that the dominant error in our bosonic systems, like a superconducting cavity, is single photon loss, right? This code cannot be used to correct single photon loss, and a single photon loss will be like a dominant error that flips your qubit from one point in the Bloch sphere to the other side, and any type of dissipation you can play with would not be able to correct that error in this particular two-component Cat state encoding. So we want to do a little bit better, and let's just try to address this problem head on and see if there's any hope we can do this. We work with a bosonic qubit. Again, this is a bosonic qubit symposium, right? Let's try to do dissipative error correction for a bosonic qubit against the main enemy we're facing, which is single photon loss, as described by A. This is the error we try to battle. So first step, you need a code against that, right? You need a code that can address can correct single photon loss. So we use this code, which is well known to many of you, from Liang's talk to Steve Gervin's talk to a few other talks. You've seen this CAT code or binomial code. And this needs to be a mod4 code, a 4-component CAT code that can allow you to correct a single photon loss. And now we just sit down and ask this question. If our code space is a CAT code and there's an error space, which is an opposite parity CAT code, can we build this corrective dissipative operator acting on this error space to restore your state into this code space? That's the essence and what we do in this experiment. So here is an outline. First, we're going to talk about the scheme. It's going to take a while, but I hope to convey to you all the ideas going into the scheme and why it has a chance to work. And then I'm going to tell you about our experimental implementation and characterization of this very special dissipation operator that we call PRESPA, or parity recovery by selective photon addition. And then I'm going to move on and show you dissipative AQEC and point out some possible future directions built on this. How much time is this? 9 minutes? Okay. I will very briefly go through the basics of a bosonic 4-component CAT code, which many of you have seen. This is a Wigner function of a 2-component CAT state. This blob in your IQ space, in your phase space, represent a coherent state alpha. This is minus alpha, which is a coherent state of equal amplitude but opposite phase. So in the middle, this blue fringe is negative, okay, negative Wigner function values. And so this means this is an even odd parity cat state, which we call this horizontal cat, and it's alpha minus minus alpha. Okay, and then there's another cat state we can write, which is also odd parity, blue fringe in the middle. This will be a vertical cat. And we can use these two as, say, the plus x and the minus x basis state of a Bloch sphere. And this will give us a cat state encoding. Okay, this will be your 4-component cat state. And these two equators are 2 cats. And the other 4 cardinal states would have these 4-fold symmetric Wigner function. And notably, the 0 logical has a 1, 5, 9, and so on Fock components, and the 1 logical has 3, 7, 11. You can call this is mod 4 equals 1, and this is mod 4 equals 3. This is the encoding we start with considering. Okay, and this is a well-known fact, which is why we all sit here discussing bosonic code, because it's highly hardware efficient, right? Instead of using, let's say, a 7-qubit Steen code, you need to correct the 21 error syndromes. Now we're talking about a single harmonic oscillator and trying to attack this single dominant error, which is single photon loss. Okay, so how does error correction against single photon loss work in this code? The key is parity. Thinking about this CAD code, the entire Bloch sphere is characterized by odd parity for these CAD code states. Okay, and let's think about any arbitrary quantum state as characterized by a superposition of CG-CE coefficients working on the X basis. If we have a natural photon loss in the system happening, all of these odd components of Fock states will flip and become even, right? Recall this nice property of an annihilation operator. You're going to end up with a new state, which is CG and ICE flip into a new X state, which is an even parity cat state. So this is like a change of basis from an odd parity subspace, change of space from odd parity into an even parity space, while these coefficients will stay the same. It's because these coefficients store the quantum information. The information will stay there. As long as you can keep track of parity or you correct it, you can beat single photon loss. So when the photon loss happens, you see the parity flip from blue to red. That's from odd to even. And in order to do error correction, we typically ask for measurements. We do QND measurements of photon number parity, as first demonstrated in 2014 by the Yale group. And Lu Yan now moves on in Tsinghua, and I believe you've heard a talk by him at 3 a.m. midnight in my time. So hopefully some of you have caught that talk. Okay, so how do you, so with this tool, when you have the ability to do QND measurement of photon parity, there came the landmark achievement of QEC breakeven, which encodes this experiment, encode your quantum information in the logical qubit in a photonic cat state, and achieve the logical lifetime, which exceeds the native lifetime of this cavity by about 10%. And I'm not going to show data here. I would like you to focus on this fact. This is the flowchart of that experiment. And these smart and hardworking people were like sitting in the same room as me, working diligently for a few years. And this whole decision tree involves FPGA programming very heavily. And there are real-time waveform calculation, adaptive operations on the fly to get this to work. And it took Nissim, a very talented postdoc at the time, almost 3 years dedicated to make this FPGA system working. It was so impressive that he had to move on now and build his startup company on this hardware system. You can check that check that out. Quantum machine, I know there's like $20-something million venture capital money poured into that because for them to sell basically this control system. So we really don't want to do this, especially for like a young group like us. We often don't have the resource to do complicated things like that. Well, unless you are Lu Yan, then you can do that. So my message is active QEC is really control resource intensive. So can we really dramatically simplify this? Let's try just to make a wish, dream big. Can we add a time-independent dissipation to the system? Okay, to take care of all that, we add a time-independent dissipation. This dissipation says the following: whenever parity flips, we want it to be odd. It somehow flips even. Whenever it flips to even, just to flip it back. By the way, we need the right phase. Don't scramble the phase. This is what the name of this dissipation. Okay, so furthermore, we are kind of limited in our engineering capability, and we only have this type of device, and we want it to work like right away in an existing device. That's basically the workhorse of many of the bosonic QEC experiments in maybe not today, but a couple years ago. And this is a superconducting 3D cavity, 3D circuit QED package. You have a transmon ancilla qubit right there that's coupled to two bosonic modes. This would be your high Q storage cavity where you want to put the fancy cat state in. And this is a low Q cavity, which is used for dispersive readout of this transmon qubit, which can encode or decode or control this bosonic qubit. So this transmon is this cat states ancilla, and this is this transmon's readout resonator. The Hamiltonian will be written like this. That's your dispersive Hamiltonian, or James Cummings Hamiltonian in strong dispersive limit. You get this Hamiltonian. That's your cavity A, the bosonic qubit cavity, and this is your readout cavity, and this is your qubit. And then you have this key term, dispersive interaction between the qubit, between the transmon and the cavity. Then you have some higher order nonlinear term, the Kerr term of your storage cavity, which we often don't want. So can we try to make this work? Let's try to produce some dissipation. We want this to be continuous wave drives to produce a constant dissipation to the system to do error correction. So I think many people thought about this, and if you ask Mazia, he will tell you, no, you can't continuously project on parity with dispersive Hamiltonian. You really need some fancier Hamiltonian, which is of the parity form, like a pi A dagger A. This is your parity operator interacting with your qubit. You cannot just have dispersive interaction and hope for a continuous projection on the parity subspace. So there almost seemed like no hope, but we just tried a little bit harder. We cheat. So how do we cheat? Let's just say this. First of all, let's truncate the state. Let's get rid of 9 and above, which is not too bad. Actually, all the existing experiments kind of truncate the cat states. If not truncate, they work with very small cat amplitude anyway, right? So let's just focus on 1537. Then let's try to ask for this dissipation. If the state drops from 1 to 0, let's move it back to 1. And if it goes from 3 to 2, let's make a dissipation to dissipate the 2 into 3 and 4 to 5 and 6 to 7. Okay, so we don't ask for like infinite level parity operator. Let's just work out these 4 states. So how do you make a dissipation that adds a photon in the system? This is actually a fairly standard playbook in reservoir engineering. What you want is a sort of a pumping scheme, right? You find a dissipative ancilla in the middle, okay, and you put coherent drive on from 0 to some 1-photon state while exciting this dissipative ancilla. And if this ancilla dissipates, it's lossy, you're going to get to the 1 state, right? This is the basic scheme of adding a photon. If you can do this with 4 parallel paths, you do this path independently, then you will be able to implement such an operator. So this process involves exchange of 2 excitations. Yeah. So this can be done with a 3 or 4-wave mixing process in your system if you have that, which we do have in superconducting qubit. But there are 2 major issues here you have to think about. One is that, as I said, your dissipation, whatever you put on the system, it has to really respect the code state. You cannot do anything bad to the code state, right? Imagine if you're in the 1 state, and if you try to do this 0 to 1 E drive, chances are you're going to get 1 into a 2E as well, right? So you must avoid destabilizing the code space. So the way to get away from this is to use dispersive interaction. If your ancilla has a dispersive interaction with your bosonic states, that means you can get these transitions to be at different frequencies, and same as this 1 to 2E. You can make this a little different frequency. You drive this selectively, then you can avoid destabilizing your code state. That's why we call this parity recovery by selective photon addition. But now you stare at this diagram again, you notice the second problem. These slopes are not the same, right? If I make these transitions, they are at different frequencies. Now the dissipation back down to my code states, these emissions will be at different frequencies. So that means the environment, the dissipation of your ancilla will tell the environment which path you've taken. If the environment eavesdrop on you to know which path you're taken, it's going to completely dephase your superposition in your bosonic state, right? So how do we do this? We must require the emission process to have identical energy. It must emit identical energy. So we came up with this called path-independent 2-stage pumping process. This actually fixes this problem, and it works in this following. Now we have these blue states are our code states. These are odd parity states, and the red states are error states, 0, 2, 4, 6. This is our system and Hamiltonian. Now think about if the cavity is in 1 state and it lost a photon, now it goes to 0. So how do we fix it? First, we have a drive. It's a simple qubit drive, which is just Q dagger Q is our bosonic raising and lowering operator of our transmon. So it's very enharmonic, but we still like to write it as a raising and lowering operator because there are 4-wave mixing processes. It's easier to write it this way. So this is a simple transmon excitation, but we do that frequency selectively, so it doesn't drive this 1G0 to 1E0 state. There is a small frequency shift down between these dispersive frequency shift to make sure we only drive this transition. And now we add a 4-wave mixing drive, which excites the cavity from 0 to 1 state and de-excite the qubit or the transmon from E to G, while also adding a photon to this reservoir mode or to our low Q, this readout resonator mode. Now the readout resonator is dissipative, so it's going to quickly relax to 1G0. This will allow us to add a photon to fix the parity from even to odd. Okay, now we do this 4 times. We basically put 8 microwave drives there. These are like four tones in a comb, and these are 4 tones in a comb. Now we can fix all these red states and back to the even states. And the nice thing here, you're going to see we do all these drives selectively so that we protect these code states. And they have different frequencies differing by the dispersive shift we call chi-q there. And these 4 drives are also at different frequencies. Actually, they are exactly compensating in the frequency difference for the second between the first comb and the second comb. So at the end of the day, these 4 emissions are roughly at the same frequency. They only differ by a very small amount, which is the cross-current interaction between the storage cavity and the between the storage and our readout cavity. That's a relatively small higher order nonlinearity in the system. So we managed to produce like an equal emission frequency. This would allow this process to be phase coherent between these 4 paths. So ultimately, if you just in your mind approximately eliminate all these intermediate dynamics, you're presented with this simple way of thinking of things that's just a dissipation operator acting on your bosonic state, which is a conversion of 0 to 1, 2 to 3, 4 to 5, 6 to 7 coherently. And if you can make sure these drives these are all lambda, these are all omega, they have the same drive strength, and all the dynamics happen completely in sync parallelly, then this is all phase coherent and with equal rate and so on. So this is our PRESPA or PRESPA operator, parity recovery by selective photon addition. Okay. Before you complain, I will admit that this is not strictly a completely legal error correction code. So there's a little bit of a small issue. So imagine you have a cat state. Let's say we start with an equator state or X state that looks like this. It's a horizontal cat. And think about this limit where our engineered dissipation, that's the rate of this engineered operator, is much greater than the single photon loss rate, kappa there. Imagine you have a photon loss jump. That's a parity flip in your system. Blue becomes red, parity flip. Now, this loss operator will immediately fix it, add a photon in. But and take a look at here. There are no coefficients over here. So the system won't know which path it's adding a photon to the system, but you do end up with one more photon in the system. So you actually gain energy in the system. It becomes a slightly bigger cat. And on the other hand, if time evolves, no photon loss happens, as you know, there's no jump evolution in the system. So your parity don't change, but your original odd cat will become just a slightly smaller cat as time evolves. So when you lose photon, you get bigger. When you don't lose photon, you become smaller. So this pure state to start will become a little bit of a statistical mixture. But it's very important, and I think it would be nice for theorists to like derive this all through. Statistical mixture of cat states. In this case does not represent like huge amount of loss of information. This is because your information is stored in like the phase space axes, right? The information is stored in the phase of your cat state, whether you're horizontal cat or vertical cat. Whether your cat like drifts a little bit bigger or a little bit smaller, it doesn't matter. It is entropy, but this entropy doesn't really spoil the information. So we can actually retrieve this quite smartly with a size insensitive decoding process to get the information back. Okay. I spent majority of the time to tell you about the scheme, but now we're going to show the experiment. This is our device. We have a 3D package, and this is a coaxial shaped storage cavity. There are actually 2 modes there. We just use one mode. That's our storage cavity mode A. Coherent lifetime is T1 time is 500 microseconds. And we have a transmon in the middle. This is a reasonable transmon, not great, but sufficient for this experiment. There is a relatively high excited state population, which will come back to bite us because that causes uncorrectable error. And the dispersive interaction is 1.3 megahertz, which will be the dominant time scale in our system in setting, in deciding on how fast we can do things. And many of other pumping rates will be substantially smaller than this. And the dissipation rate is also smaller than the chi in the system. So This is a relatively standard dilution refrigerator and control scheme. And most notably, we do have a parametric amplifier, but we are not experts in readout, and we didn't really bother to optimize too much. So we don't do single shot readout. We don't have a single shot readout capability. We cannot figure out G or E on the fly to decide on what to do. So this will be a death penalty for most QEC experiments, but not this one, because we don't care what the result is. The system takes care of itself. And we use some sideband modulation with 4 different IF frequencies to generate this 4-way mixing comb and to generate this qubit drive comb. And all these 4 fingers of these combs can be individually adjusted, which is kind of important to make the scheme work. So now let me show you a simple thing, a dissipative 0 to 1 conversion. Imagine you start from, let's just look at this box. If we start from a 0 state, which is your natural vacuum state in the system, we turn on our comb. This is our PRESPA operator, or 8 microwave tones apply constantly to the system. And after a while, we do transmon spectroscopy, which is basically our analysis tool to figure out what is the photon state in the system. Okay, so you see here, x-axis is the transmon frequency and y-axis is time. You see the transmon frequency start from no detuning, which indicates the cavity is in vacuum. And after a while, there is a transition process that it moves to 1 chi shift, which tells you the cavity gets to the 1 photon Fock state. And importantly, it doesn't switch back, which will be a coherent coherent swap process. And it doesn't substantially leak out of the 1 state either. At t equals 0, we get a 0 photon nice Fock state or vacuum state. And after 25 microseconds, it's essentially a very good 1 photon Fock state. And it stays there for the most part. Okay, now can we do more? Can we apply that to a even superposition state? Okay, in this experiment, we rely on OCT pulse, which is computed, provided by our theory collaborators at Northwestern, by Jens Koch and his student Brian. This method is sort of well known in the field now, following an earlier paper that demonstrates, essentially it's a bunch of numerical pulses with 2 basebands, 1 on qubit, 1 on transmon, 1 on cavity, that can basically give you any state you want. So we use this pulse to prepare this even parity superposition state. Okay, it's actually even parity cat state. And we turn our 8-tone pump on for a while and ask, what do we get? And dun-dun, that's what you get. It becomes a 1357 state. Of course, this doesn't prove superposition, but it just gives you an idea that all these states gets actually added by 1 photon. Now let's take a look at time domain. Okay, we in this case for 0 to 1 conversion, this will be just a trace, a cut over here. We start with a 0 state, and we turn this on, and we measure the population of a 1 state over time. And you see that this conversion starts from no population in 1 state all the way to almost full population in 1 state over a time scale of like a little bit less than 10 microseconds. We can do the same thing for 2 to 3. We prepare 2 state and ask for how much 3 state do we get. And we can prepare 4 state and see how it converts to 5. And we can prepare 6 and see how it converts to 7. And we tune the parameters basically to match the shape of these curves. That will tell us, we can figure out what is the drive rates, the transmon excitation rate and the 4-wave mixing rate. We match all these numbers together to achieve basically indistinguishable transition paths. They're a little bit different in the final efficiency, because the higher the photon number you're dealing with, the more natural photon loss you have to compete with. That's why you end up with lower fidelity at higher numbers. Okay.
And just to let you know, 5 minutes till questions.
Okay, sure. Yeah, I think I will. Yeah. Let me go ahead. I'll skip the outlook part probably. this is now we've shown population conversion, right? But how about superposition? Now let's prepare some superposition states. These are all 6 pairwise possible superposition initial state we prepare with OCT pulse. Now after 25 microseconds, this is what you get. These are the Wigner functions. You can see all your red origin points now become blue. That's an even to odd conversion. And the cats and these states basically grow by a photon into these states qualitatively. We can do Wigner, we can do density matrix reconstruction and figure out the off-diagonal elements. And the off-diagonal elements ratio basically tells you roughly the efficiency of this conversion. It's not great, but you get a little bit over like a 2/3, in roughly about 2/3 for this for these superposition conversions. And with this kind of measurement, we can prepare all sorts of initial superpositions and basically to do a process tomography. We want to figure out, characterize this dissipation operator. How good is it to compare with your ideal PRESPA, right? This is the process matrix we can figure out. And this part basically tells you the population transfer part. You see the 1 state preserves and the 0 state, the even states grow by 1. And the off-diagonal elements also have this even to odd coherence in this conversion process. And odd parity states will preserve their coherence. And then there's some error terms. This is our characterization of a cavity dissipative process. So now in the final moments, show you some data. If we apply this this magic dissipation, corrective dissipation operator to a set of code states. These are the 6 cardinal states of our truncated 4-component Cat state. Okay, these are the initial state, and over some 140 microseconds, which is roughly like the time scale of losing a single photon in our M bar of 3.5 bosonic state. And you see the Wigner function is smeared a lot. And if we turn on our pump tone, we turn on our operator over 144, you can see the features are preserved much better. And in particular, the parity is great. The parity is actually fairly well preserved. There is some dephasing process going on, but this is much better than the uncorrected situation. So we're going to do another thing, which is to decode the state. So in this measurement, we want to be more quantitative. So we would encode our state to these to the bosonic states and turn on this error correction dissipation. And after a while, we decode it and we measure what the qubit state is. This decoding involves a little bit of a careful consideration to retrieve a little bit more information. I'm gonna skip that part and just to take a look at the result. This is our transmon. Transmon's capability to retain information set by its coherence time, right? And if we encode our qubit into our truncated Cat state code, and you simply just wait for some amount of time and decode and ask how much information you retain. And this information storage gives you about a time scale of 130 microseconds. And now with error correction, with this continuous dissipation, we boosted the lifetime by a little over a factor of 2. So unfortunately, just as the same exercise as a few other studies, you can compare this with the simplest encoding, uncorrectable encoding, which you can dump your information to the cavity superposition of a Fock 0 plus 1, 0 and 1 encoding. So this is not yet achieving a break-even yet, because in order to do error correction, you always pay penalty, right? You either use more qubits or use more photons. So in this case, we pay a penalty of about 3.4 times to start, and then we gain a 2.2 times. So the efficiency of this experiment is not yet at break-even point yet. So there are many, I can give a full lecture of what are all the things that can possibly go wrong in the system. But just to very briefly talk about this, one is photon loss is the dominant error we want to think about, but it's not the only one. And in particular, you've heard again and again, blame the ancilla. Ancilla is the weak link in the system. And in this case, ancilla is hot. A hot ancilla with dispersive interaction is especially bad. So even if there's no single photon loss in the system, your cavity still get hurt by the ancilla. So this is what happens in our system. And the second thing is the PRESPA has the ability to correct single photon loss, but it doesn't succeed 100% of time. So we find that it roughly succeeds 3 out of 4 times. For the other quarter of the cases, what happens? Either the second photon loss happens, or your ancilla relaxes during the correction, and so on and so forth. And these will give you problems. Okay, so these are okay.
Just 1 minute into question time, Chen. So.
Okay, sure. So we did break-even math. So with very realistic parameters, if we do a little bit better job to get our transmon T1 and T5 up to the standard, up to industry standard for 3D transmon, and the system should be able to tolerate some reasonable imperfect thermalization system while still reach break-even with a reasonable percentage. And in the future, I just want to say okay, I'm gonna skip this and to my summary page. So to summarize, I've shown you a quantum error correction of photon loss, which is a dominant error in bosonic system, with an engineered dissipation operator like this. So the ability of this is to dramatically simplify a control scheme look like this into basically turn on a constant dissipation pump to the system to correct the photon loss. And this is kind of like a passive protection by a continuous always on dissipation. So it has a link, a connection to people talk about intrinsic protection that you built into your qubits. And furthermore, just to emphasize what this is and what this isn't, I'll emphasize that this is a constant dissipation that we apply to the system, which affects the error space to fix it, but doesn't destroy the code space. This is different. It's connected, but it's not the same as you do unitary operation plus reset in a scheduled duty cycle. This is a constant dissipation at all times. And the goal for this line of research is to build and improve a logical qubit in a single mode. This is different from producing a noise-biased building block for next level of quantum error correction. So this is our archive paper, and you can check on that. And I'd like to thank my graduate student, Jeff Girdler, who really is the main person responsible for make all this work. And Shudi is a junior graduate student participating in the numerical analysis of the experiment. Julian, my former postdoc, was responsible for fab and a lot of the cryogenic work. And I'd like to thank Jens Koch and Brian Baker for their some theoretical work and the OCT part of the project. And finally, we have positions open for new postdocs and graduate students. If you're interested, please contact me. Okay, yeah, thank you very much.
Yeah, well, thank you very much, Chen. That was a very exciting talk. I think we have time for at least one question. Ben has a question here in the chat, asking if you're potentially able to tune the relative weightings in the dissipation operator, or are you confined to unweighted raising operators like the Susskind operation?
Yes, we can tune the weighting of all 4 components in this in constructing this dissipation operator. But I would say we believe there's no benefit really to make them to be unequal, because if they are unequal, you are going to the environment is going to know which path it's taken in addition to the natural photon loss A. And the timing of the loss will leak a little bit information. So we can certainly do that, but it's unclear if that can give us any advantage in for QEC purpose.
All right. I mean, Ben might have some follow-ups for the Slack about that, but I think now one last time, thank you, Chen, for the talk, and I think it's time to move